Today's session is sponsored by ATA Engineering, and the title of today's session is Automated Structural Design Optimization for Everyone. My name is Scott Thibault from ATA Engineering, and our guest speaker for today's presentation is Dr. Chris Ostojic, also from ATA Engineering. Just to give you a quick introduction to ATA Engineering, we are a high-value engineering services provider, providing expertise in design, analysis, and test. And we serve a great number of industries: aerospace, robotics and controls, themed entertainment, defense, industrial mining equipment, marine, consumer products, and many others. So if the software that we're showing to you today is of interest, we can certainly talk to you about that. But if you also have engineering challenges and need help with those as well, we have the engineers and the expertise to help you. In addition to being a high-value engineering services provider, ATA is a value-added reseller for Siemens digital industry software. We are, in fact, a platinum-level solutions partner for Siemens, offering a wide number of products, including those we'll be seeing today, which are HEEDS and Simcenter 3D. But we also offer NX CAD and CAM, Solid Edge, Star CCM Plus, VMAP, Teamcenter, and many others. If you have need of engineering or CAD software, please feel free to contact us at the number shown here. And you can also get access to a number of valuable resources on our website, ata-plmsoftware.com. The website provides access to a wide number of resources, white papers, macros, presentations, recorded webinars like today's, and many others. Please feel free to visit it and use the resources that you find there regularly and share them with your friends. So I'll now turn over the session to Dr. Ostojic, who will give us a rundown on how anyone can do automated structural design optimization.
So as Scott mentioned, my name is Chris Ostojic, and I'm going to show you how we can use HEEDS and Simcenter 3D to optimize a vehicle component. In this case, it'll be a helicopter component. Talking about broadly about aerospace vehicles, lighter is generally better. Aerospace vehicles place a premium on low weight. Also, their consequences of failure can be catastrophic when you're in flight. So margins of safety must be met. Increasing these margins usually means having to add additional material and thus creating heavier aircraft. Helicopters, such as the one shown in the upper right, are particularly complex and require many mechanical components, and manual redesign of these components to maybe make them lighter is costly and requires a lot of man hours and time. So automated multidisciplinary optimization can be used to reduce weight while maintaining safety margins and limiting engineering time, and that's what I'm going to show you. So the example I'm going to show you today is a helicopter blade grip. The blade grip is required to hold the helicopter blades to the rotor hub, so it's very important. The blade rotation, lift, drag, and pitch adjustments produce high frequency, high amplitude cyclic loads on the blade grip, and blade grip failure would be catastrophic, but weight savings of this and other components are still desired. So I'm going to show you how, with HEEDS and Simcenter 3D, safe weight reduction of the blade grip can be obtained by intelligently selecting and evaluating hundreds of design variants in an automated workflow. So here is our baseline blade grip design. So variations from this baseline design are going to be created by modifying 8 parameters, and the performance measures of our optimization will be based on mass improvements off the 35.3 kilogram baseline design. So to create both the solid model of the part and also mesh and run the analysis, we're using Simcenter 3D, which seamlessly makes model changes and then remeshes the FEM after each geometry change before running an analysis. Design parameters are exposed within Simcenter 3D so that HEEDS can see them through the use of CAD expressions, which is what I'm showing in the upper right-hand corner. Simcenter 3D modifies the geometry and meshes the FEM, again, seamlessly, and that's what I'm demonstrating on the bottom here. I've changed the parameter extrude width from 150 millimeters to 190 millimeters, and Simcenter 3D makes this model change and remeshes automatically. For the loading, well, all the loads on the blade grip come through the helicopter blade. We're not modeling the helicopter blade explicitly, so we're using these rigid elements to apply loads to at the lift and drag center, which will then be transmitted to the blade grip. The bolts attaching the blade grip to the blade are represented by C-bar elements and connected to the grip with RBE3 elements. And then these constraints constraining the blade grip to the rotor hub are represented by RBE2 elements. And you can just see the loads here and the distance from the blade grip that they're applied over in this table here. The axial force is the overwhelming load in this case. So I was just going to switch over to Simcenter 3D real quick and show you, this is, again, the model that I was showing in the slides. And it's very important that the parameters are made into expressions so that they can be exposed to HEEDS. And then in Simcenter 3D, we use this model to create the FEM and simulation, applying the loads and the constraints, as you can see. Yeah. So here's our computational model. In Simcenter 3D, we're using NX 1899. We're using solution 101, which is a linear static solution. And in this example, we're just solving this serially. It's a pretty small FEM, so we don't need to run in parallel. We're using a titanium alloy, and here are the properties here. The fatigue limit is 880 millipascals, and in our design, we're going to want to design with a factor of safety 2 on that fatigue limit. And then the mesh, as I mentioned, is small. It's 482 tets for this baseline case. It might vary, by a few with different design variants. But again, you can definitely scale this up. This is just a modest size model that was used for demonstration cases. All right, so now we take a look at HEEDS. HEEDS has a proprietary algorithm called Sherpa, which performs design space exploration by searching parameter ranges intelligently to determine a minimum mass design in this case. So what HEEDS is doing, we're telling it to search parameter space defined by these 8 parameters in these ranges here. And we want to look at these 2 responses, mass and von Mises stress, with the objective of minimizing mass and the constraint that we want to keep that factor of safety of 2 on the fatigue limit, so von Mises stress less than 440 megapascals. I'll point out that an exhaustive search of this design space results in 454 million simulations. But the good news is that Sherpa finds a significantly improved design after just 200 evaluations. And furthermore, it does this automatically without analyst supervision. So HEEDS setup is made easy with the Simcenter 3D analysis portal. This is what HEEDS looks like when you open it up, and I'll give a little demo in a second. But all you do is select the licensed Simcenter 3D portal, and that makes the setup the rest of the optimization problem much easier. So I'll just hop into HEEDS here real quick. So I've just got a blank simulation here. Blank case here, and I've got this generic portal here. So I'm going to say no. I'm using Simcenter 3D. So I'll select the Simcenter 3D portal. It then recognizes the execution commands that needs to run, and then I say, okay, I need to point to my input file. So got the input file from my Simcenter 3D model. It just launches Simcenter 3D to parse the file for all the inputs. So what it's looking for are the accompanying FEM and part files. And it knows, since we're using Simcenter 3D, that these should be accompanying the Simcenter 3D sim file. So it's going to populate those here. It also knows that, hey, all of the analysis results are going to be in this output file, which for Simcenter 3D happens to be the same as the input file here. It then pops up with this window saying, do you want to auto tag this? So it recognizes, hey, there's going to be some input variables and some responses that you're going to tell me to recognize in the Simcenter 3D file. So I say, yeah, I want you to auto tag. And then I can go in here and pick out the CAD expressions that I want to vary. So in this case, I'll just pick, cut depth and base diameter, for instance. Then I go to next, and I can say, okay, I want to vary this from 200 to 240, and this, from 190 to 230. And then it says, okay, now what responses do we want? Again, we want to monitor the mass and the von Mises stress. And so it's as easy as that. Now we go through and we say, okay, we want to run an optimization study by varying these variables like this. We've already tagged it, so that's fine. And then we want to monitor these responses. We're going to say we want the mass to be an objective where we want to minimize mass, and this will be a constraint where we want to keep the stress below 440. We then go over and say run, and HEEDS starts the run. I forgot to mention that we can tell it how many evaluations we want to do. In this case, we're doing 200. So as HEEDS is running, it keeps you updated on its progress. So you can see here that it keeps track of feasible designs, those that meet the constraint, that stress constraint that I set. Infeasible designs, those that, the analysis completed, but maybe it results in a von Mises stress that's above 440 megapascals, so that's not feasible for our purposes. And then also, there may be some designs that just error out for some reason. You know, maybe the dimensions that we specified are incompatible, or there was some just issue with the analysis. So it keeps track of these. Even when it hits one of these error designs, it doesn't stop the optimization study. It just says, I'm going to ignore this, and keeps on going. You know, here it's just reminding us what our optimization problem definition is. This shows kind of a range of the parameters and responses that have been looked at. And here's just a histogram just showing the distribution of the masses of the designs evaluated so far. And this little animation on the right just shows some of the design variants that we've analyzed. So here I'm showing this objective history. And so as you can see, HEEDS explores the design space to drive towards some objective, in this case, minimum mass. The blue dots are all the feasible designs. The red dots are all the infeasible designs. So you can see that it searches a large number of designs, and it doesn't just search, you know, really close to. It doesn't just search designs that are really close to one another. It kind of jumps around because it's aware that there are both local minima and global minima, and it doesn't want to be, you know, stuck in a local well when maybe there's a more optimum solution somewhere far away in the design space. You can see that in the first 9 evaluations, it found a design that had dropped the mass 16.7%. And then, you know, it just kept on chugging and finding better and better designs. And after 188 evaluations, we find our best design, which is 21.1% lower mass than the baseline. Again, I just set it to stop at 200 designs, but maybe if we set it to 1,000, it might improve on this further. So, along with the optimization algorithm, HEEDS provides very powerful post-processing tools. So here you can set up this kind of layout, which can help an analyst identify trends and show common features of the highest performing designs. So this up here is called a parallel plot. I'll describe that a little bit later. This is a self-organization map. It kind of shows where the different populations of evaluations lie in relation to one another, and then you can just, you know, display a plot of the current result. This happens to be our best case design. One of the post-processing capabilities is correlation table. So this correlation table quickly shows relationships between parameters and responses. And this can be useful. For example, in this case, the cut depth parameter, it has, you know, a non-zero correlation with mass, but very little correlation with stress. So an analyst can say, okay, this is a knob that I can turn by changing this cut depth to really affect my mass without really having any effect on stress. HEEDS also allows you to, the post-processing also allows you to investigate alternate designs. So here I've got this parallel plot, and on this plot, the gray line is the baseline design. The yellow line is the best design, and this kind of shows how these designs, you know, how they performed. On the left here is the resulting mass, and then the rest of these fields are the parameters. So it's showing how these parameters are varying with each one of these designs. And so what I've done here is I've taken the 5% designs that are all within 5% of the best design here, and I say, okay, I want to see their similarities. Maybe maybe the designer is looking for a design that is under specific manufacturing constraints that the best design may possibly not meet. He can search these family of designs that are very similar in terms of their resulting mass, but might have different parameters that meet the manufacturing constraints. You can see that among these best performing designs, a lot of them are very similar in most of the parameters here, but there's large variations in extrude width and large fillet radius. So these are maybe parameters that a designer can play with to make it maybe more manufacturable or meet some other constraint that they're looking at. So in this particular case, this took under 4 hours in a serial run on my desktop computer, and improved the design by 21.1% mass over 200 evaluations with very little setup on my part. I was able to also just push go and go do something else. In this case, it was just the end of the day, so I stopped working and the computer continued working. If this was manually investigated, though, these 200 evaluations would likely take someone who is very fast, maybe 50 hours to modify the part, remesh, run the simulation, and document the results. This is not even taking into account that HEEDS and its Sherpa algorithm searches this design space intelligently. So it picks the new designs based on the history of the already evaluated designs. So an analyst would also have to do those computations if he or she wanted to, meet the performance of HEEDS. So in summary, what we were looking for was a weight-optimized helicopter component, and we employed HEEDS design space exploration software with Simcenter 3D to find a better design automatically. Our results in this small study was a hands-off method, pretty much, that produced a design with a 21.1% reduction in component weight while achieving positive margins with a factor of safety of 2 on the material fatigue limit. Conclusion, HEEDS and Simcenter 3D produced an improved helicopter component design on a desktop computer with minimal effort from me. And on the bottom here, I'm just showing the baseline design and the final design. So that's the end of my presentation, and I can take any questions.
Perfect. Thank you, Chris. So I've updated the meeting settings. So if you're called in today, you can now unmute yourself if you'd like to ask a question out loud. We can also take questions through the chat. But I think one of my first questions is, you mentioned that this was solving serial, which probably makes sense in this case because it's a part it looks like it would solve pretty quick. I think that means that it must, if it was 200 solutions in 4 hours, it took about a minute per solve. But imagine you had a much bigger model that took longer to run. Can you solve these in parallel?
Yeah, you can solve these in parallel. I've done HEEDS runs with fluids problems, so not using Simcenter 3D, but it has no problem shooting off jobs in parallel. But yeah, using Simcenter 3D, you can also run in parallel. You can also run multiple cases in parallel. So if we were looking at this part or a similar sized part, and we wanted to run, many evaluations, and that can be done much more quickly than by shooting off simulations in batches of 8 or so, and those can be run in parallel. The results will be returned, and the optimization algorithm will take that information to shoot off the next 8.
Yeah, I've got a question. I have run a number of these types of stress optimizations using Simcenter 3D and also other software tools. And oftentimes I will find that the optimizer focuses on unrealistic stress hotspots that are just an artifact of the discretization that an analyst would simply ignore. Can you comment on that, how to avoid these stress hotspots in corner regions where a fillet may not be appropriately modeled, or those types of things?
You can, yeah, thank you, Peter. You can tell HEEDS to, when it looks at, say, that von Mises stress that I was outputting, you can tell it to ignore certain element IDs. So, you know, it takes a little bit more work up front by the analyst to say, okay, these element IDs are maybe in a range that that would be, you know, that would have these stress hotspots, and if you could just ignore these and concentrate on the more realistic stresses, then that wouldn't affect the optimization.
So in your case, you morph the mesh, then you don't remesh, because if you remesh, then the mesh element IDs go all over the place. They don't stay constant.
Right, yes. As I was saying that, I realized that that would be an issue. So that would be something that I'd have to look at in Simcenter 3D, but I'm sure that there would be a way to filter, you know, spatially filter it so that these hotspots did not pop up in the results that were passed to HEEDS.
Yeah, and I think I have kind of two thoughts to add on there. My first is that, you know, it would be common for us to say, well, we don't want to look at results and elements that are attached to RBE2s because those introduce artificial stiffness. You can get some unrealistic stresses there. So maybe you select the elements, like in this case, around those bolt holes. And if you lock that mesh, then that mesh wouldn't update whenever it would remesh based on geometry changes. So I think in that case, I think you could specify those element IDs as elements to ignore in the optimizer, and I think those would stay consistent. But then I'm thinking that you also might be able to do something where you put like mesh controls on a fillet radius or something. So maybe the concern is when it remeshes, maybe it won't know best practices of things like we want 3 elements across our fillets and things like that. So I imagine if you went into the FIM and you put that mesh control in, I think it would remember that across geometry updates and remeshes too, in which case that might help make sure that your element quality stays consistently high from run to run.
Yeah, those are all the kind of the tricks of the trade that I've been trying. Okay. I just wanted to see whether there's a magic bullet, but it looks like there isn't.
Have you been doing this optimization process in HEEDS, Peter, or with some other tool or some of the?
Oh, I've been in the field for 25 years, so I've used Nastran, Simcenter, ANSYS Workbench, and all the optimization tools that are out there. So depending what the favorite tool du jour was of my employer at the time.
Well, I think this is an interesting question you raised, though, and I think that we'll pose it to the tippity top, you know, high altitude nosebleed experts at HEEDS in the HEEDS team of Siemens, because it can't be an uncommon problem.
No, it's a very common problem that I've encountered a number of times.
So I have to believe that the HEEDS team has seen this many times before, and maybe there is a solution within HEEDS that might not be commonly found in other, you know, built-in optimization schemes, because HEEDS really is kind of unique in a lot of ways, and that might be another one. So why don't we look into that for you, and one of us will get back to you on it.
All right.
And thanks, Scott and Jonathan, for chiming in there. One more idea that I had, thinking about it while you were speaking. So in this example that I showed, we've got this one process. We've got a process with this one kind of analysis in it, but you can stack up a bunch of analyses or a bunch of tools in this process here. So there could be, you know, maybe some sort of script that you put in, like a Python script or something that does some filtering again, this would be designed by the analyst who would know, okay, these are areas that I'd want to skip or something, but maybe it would be able to filter out these problem areas before being passed to HEEDS.
Chris, can you comment on multi-objective optimization? Like, I'm thinking, what if you have multiple parts and maybe they have different materials and different allowables? So maybe each one has its own individual stress goal, or you're trying to check stresses and deflections, or how does HEEDS handle things like that?
Yeah, so yeah, what I showed was a single objective optimization. In the case of multiple objective optimizations, yeah, you can have competing design, well, I guess, objectives. In that case, HEEDS will search that design space and try to form a Pareto curve so that the analyst could then look at that curve and say, okay, what's the best trade-off between these competing objectives? And that can work for not just two, but many design objectives. It just increases the space of that Pareto front.
So do we have any more questions this afternoon? Because if not, we'll end the session and the recording.
One quick one regarding parallel execution. I assume that would tie up a number of Simcenter licenses then, right?
Yes, you would be correct. If you want to run 5 or 10 Simcenter simulations simultaneously, it would require to have that kind of license.
So for in the real world, where licenses are always tough to come by, that is usually the limiting factor for us running anything in parallel, because we run out of licenses.
Yeah, I certainly understand. I'm sure you can limit how many simultaneous cases are done. So if you have, for example, 3 licenses you can use and you want to run 300 cases, you can tell HEEDS to run only 3 at a time.
Right.
The other thing you might want to consider at some point, if not immediately, is the token-based licensing from Siemens. So you get a bundle of these tokens that will allow you to use different capabilities with a great deal of flexibility. That might
I'm not sure. I'm aware of the tokens. I'm not sure we're using that right now or we're about to switch to it. I think everybody pretty much is moving to the token-based system. So we may already be there, but I'm not 100% sure.
The way people usually use tokens is to give them access to a lot of different, very high-end capabilities in Simcenter 3D without having to individually license these different, in some cases, quite expensive modules.
Right.
But once you do have a big pool of tokens, then you have the freedom to run 5 of the same thing or 10 of the same thing, as long as you have the cluster resources available.
And as long as the colleagues don't need them at the same time.
Yeah, you can have fist fights by the water cooler over who's hogging all the licenses.
Not right now, because we're all working from home.
Everybody's from home. Yes, quite right. Thank you, Peter. Well, I think is there another question?
I was just going to add to that maybe on weekends or something where the license utilization is lower. That's one nice thing about HEEDS, is that it's automated. And it's also tolerant to failed simulations or something. So you can run it over the weekend. If it can't get a license, then it's tolerant to that. And if it can get the licenses, maybe when other people aren't using them, then that's the great thing about it running automated, running automatically, is because it can run when nobody else is working.
Well, and even if you do have to run 1 at a time for lack of licenses, it manages that process just as well as if it were running 10 at a time.
Right.
It's built for managing that sort of thing. But thank you very much for your question, Peter. We're going to end today's session and the recording. But thank you all for joining us. And if you have any further questions later, feel free to contact us. And we'd be happy to answer them then. And we will follow up with you, Peter, on this particular question if we can get some more clear direction from our colleagues at Siemens.
Yeah, thank you for your time. Appreciate it.